Okay, now for part 2 of chapter 18, we're going to wade into Coulomb's law. Coulomb's law describes the force between charged particles. And basically, if you have two charged particles, the force between them goes as this constant K times Q1 times the magnitude of one charge times the magnitude of the other divided by R squared. And this K is 8.98 times 10 to the 9th newtons meters squared per coulomb squared. R is the distance between them, right? Now, if Q, if Q1 and Q2 have the same charge, whether it's positive or negative, it doesn't matter. If they have the same magnitude, their same sign on their charge, and this doesn't have to be +1 and +1, it can be +2 and +1, or +5 and +1, or -5 and -2. As long as they're the same sign, the net force is repulsive. All right. This is where we get the saying, well, in the next step is where we get the saying opposites attract. Right. So the net force is always repulsive. And so the way to think of that is this is the force from charge 1 on charge 2. This is the force from charge 2 on charge 1. Now, the cool thing is, you notice this equation doesn't mention whether it's the force on charge 1 and charge 2. Well, the forces are equal and opposite. It's just like the Earth exerts 200 pounds of force on me. I exert 200 pounds of force on the Earth. I pull the Earth up with a force of 200 pounds. Now, that doesn't move the Earth much. The Earth pulls me down with a force of 200 pounds. Makes it harder for me to get up the stairs. Earth doesn't really care that I'm going up or down the stairs. So this is Coulomb's law. We have this constant K. We'll break it out later into 1/4 pi times epsilon naught. But right now we're going to leave it as K. And so opposite charge, opposite signs, this force is attractive. Like signs, it's repulsive. We can also begin thinking that is a force field, right? A force field, not like in Star Trek. That's not what we're talking about. This is a set of field lines coming from a charge. If we imagine, if we imagine just making this charge disappear, we could write an equation for the field coming away from this that would say how much force we would have on this charge if we stuck it there, right? That's why it's a force field. We have gravitational field that you're accustomed to. Gravitational field is in fact a force field. Gravitational exists whether or not you have a person or an object or a mass there, but once you put a mass there, you get a force. Okay. The electric field is what we call the force field for charge, and we normalize it by dividing by the charge. All right. So the electric field at where you have a point charge Q is the force on that charge divided by Q. We've taken the charge out, divided it out. In the end, if we look back at Coulomb's law, right, and we divide by one of these charges, what we're left with is the force field is K times Q, the other charge, divided by R squared. Units of electric field are newtons per coulomb, right? Newtons per coulomb. The electric field points away from a positive charge and toward a negative charge. Very important to remember which way it points. Electric field points away from a positive charge and towards a negative charge. This leads us to talk about electric field lines. So if we were to look at this charge here at a point P, right? And remember, these electric field, or the forces from the charges, are all vectors, right? They're all vectors. So if we look at the charge due to Q1, it's a vector this direction. The electric field there's this is what's shown is the net electric field for both charges. If you wanted to calculate the electric field or the force on a charge, you'd say, all right, let's pretend for a minute that Q2 isn't there, all right? So what's the electric field due to Q1? Well, it points straight out from Q1, right? And then we're going to do the opposite experiment. We're going to pretend Q2 isn't there. We're going to say, what is the electric field from Q1? Pretend Q1 isn't there. What's the electric field from Q2? Point straight away from Q2. The result is the sum of those two, right? The result goes right up like that. That's the sum of those two. The electric field is a vector field. If you want to know what the electric field to a system of charges is, or a set of charges is, you add up the electric field due to each charge. So if we have two like charges, right, the electric fields look like this, and these are negative charges, so the electric field lines are pointing towards the charge. If it were positive charges, they would look the same. They would just be pointing away from the positive charge. Down here, we have a positive charge and a negative charge. So the electric fields point away from the positive charge and go to the negative charge. Here, we have no closure, right? Here, we get closure because we have opposite charges. When we look at electric forces in biology, outside of electric eels, which are pretty can produce a pretty good charge. DNA molecule is a highly charged molecule. It has about 2 electron charges per 0.3 times 10 to the 9th meters. Or that is to say, every 3 times 0.3 times 10 to the 9th is 3 angstroms, right? 3 angstroms. So every 3 angstroms you have about 2 electron charges, or 0.3 nanometers. So that's that's a pretty good charge. The other place we have charges is in water. Water is neutral, but the oxygen hogs the electrons. So around the oxygen you have a net negative. Around the hydrogens you have a net positive. The result is a dipole. So you have a little bit more negative here and a little bit more positive here at the hydrogens. And so water can actually attract other water molecules, and they can bond because the negative part here can attract the positive part there. Overall, the molecule is still neutral.